Number one, and I'm going to start with the core problems, and I'll kind of chunk this up into some different videos, but number one says draw the graph of a function that meets the following criteria. I'm just looking for a graph. We might all have some different things going on here. So I'm looking at some particular x values. They're talking about x equals 2, x equals 2, x equals negative 3, and then we have some infinities. So I'm just going to, again, say here's 2, here's negative 3, and then we can talk about what the edges are doing. So maybe using a pencil, maybe come back with a pen, but it says the limit as x approaches 2 is 0, which means as I come in from both sides, I'm getting closer to 0. I don't know if I'm coming from the top or if I'm coming from the bottom. We'll just wait on that. Now, the second part says f is not continuous at 2. So the limit exists, but it's not continuous. Not continuous options are holes, jumps, or vertical asymptotes. Now, already I can rule out a jump, because if there's a jump, the limit would not exist. And if there's a vertical asymptote, we wouldn't be approaching 0. So really it has to be a hole. So we have a hole at x equals 2. I'll come back to that again. I still don't know if I want it above or below. Then it says f of x is continuous but not differentiable when x equals negative 3. The only things that can be going on to be continuous but not differentiable, our choices are corner, cusp, or a vertical tangent. Not a vertical asymptote, but a vertical tangent. And again, that's all they tell us about what's going on at negative 3, so we get to choose, okay? And then it says, as x approaches positive or negative infinity, the y values will reach negative 1. That's really just telling us we have a horizontal asymptote. Okay, so I need to flatten out here. I want to have a corner or a cusp at negative 3. I want to approach 0 as I get closer to 2. Oh, I went up instead of down, so I'll just whoop, turn around, and then flatten out in the ends. Okay, so I did that because I just kept going up when I realized I needed to go down. That's okay. And there we have it. So just, there we go. Okay, that's number one. Numbers 2 through 5 say find all points, that would be the x coordinate only, for which the curve is non-differentiable. Non-differentiable meaning corner, cusp, vertical tangent, or any discontinuity. Okay. So if it's a discontinuity, then we'll state which type it is. And it says, if you want, think about what the graph looks like. Okay. So on number 2, I'm thinking, do we have any corners, cusps, vertical tangent, or any discontinuities? I'm going to start here. Discontinuities are holes, jumps, and vertical asymptotes. So, my question is, does this graph have any holes or vertical asymptotes or any jumps? And we find discontinuities by setting the denominator equal to 0. So there's 2 discontinuities. And other than that, it's just a rational function, right? There's no absolute values. It's not a piecewise function. So these are my only 2 points of non-differentiability. And in fact, they are both vertical asymptotes, and I know that because I cannot cancel a factor from the bottom with anything out of the top. Okay. Number 3, there's nothing to set the denominator equal to 0, but this one is a little bit easier to look at as a graph. This is a parent graph of a V, and it's been moved to the right 1. So already I know that it is not differentiable at x equals 1. It is a corner, and that's that briefly explained kind of thing. It's a corner. Okay. Number 4, the parent graph is the cube root of x that's been moved to the right 2 units. And the cube root of x was that example I gave in our notes. It's a perfect example of a vertical tangent. So I'm going to say that there is a point that is non-differentiable at 2, and it is a vertical tangent. Okay. Number 5 is a piecewise, and if you want to graph the piecewise, by all means, let's do that. I'm going to do that very quickly here, as best I can. Something interesting is happening at 1. I have the line 2 minus x to the left of 1, and then I have 1 over x coming down when x is greater than or equal to 1, and it's going to fill that hole in. So I know it's continuous. I don't see a sharp point. I don't see, so again, this graph kind of came from like this. This is that 1 over x. I don't see a corner, I don't see a cusp, I don't see a vertical tangent. But then that other key is, are the slopes the same? So we checked to see if it was continuous. It is. Now I want to see if the slopes are the same at 1. So slopes come from the derivative. The derivative of that first piece is -1. The derivative of the second piece, well, if it's x to the negative first, the derivative is negative x to the negative second, or negative 1 over x squared. Okay, so here's my derivative on the left side, and this is my derivative on the right side. I want to know what's happening at x equals 1. So the slope on the left is -1. If I plug in a 1 here, I also get a -1, so the slopes do match. So there are no points that are non-differentiable on that graph. Okay. All right. Let's take a look at number 6. Number 6 says, state the points of discontinuity. We kind of talked about this with number 2. Discontinuities are holes, asymptotes, jumps. And in a rational function, there's either holes or vertical asymptotes, and we find those by setting the denominator equal to 0. So if I solve by factoring, I get x equals 0, x equals -4, and x equals +1. Those are all 3 zeros of the denominator, which will create discontinuities in the original. They did not ask which ones are holes or asymptotes. They just said, find the discontinuities. So we're done.